Okay. Um, it's 5 o'clock now, so I think we can start. Okay, let me see if I can share my screen first. Okay, now it works. Great stuff. So hello everyone. My name is Lysandros. I'm originally from Greece, but right now I live in Berlin in Germany. Let me see if this works. Okay, I think it does. Perfect. Okay. Yeah, like I said, I live in Berlin, Germany. I came here in 2016 for my studies, and I work for a maritime tech startup called Seafair. It's operating out of Athens, out of Berlin, out of Ukraine, the Philippines, and New York City. And what we're doing there is basically creating a platform for connecting shipping companies with people that work on board commercial vessels. Yeah, it's a very interesting thing with lots of nice fit for you. Feel free to drop me a note, and yeah, we can talk about it. Today's talk, however, has nothing to do with Seafair. It has everything to do with something I worked on pretty intensely in 2019 and 2020, and it was a project that tried to replace Python's parser. I worked on that project with Pablo Salgado Galindo. Tell you about it today. Before we really get this going, I'd like to basically give you a word of caution that this is going to be somewhat of an extreme talk. I'm going to run through the material as fast as I can just to make sure that everything with parsers and compilers and Python, but not too much. And people who do not know anything about it will still have fun seeing me mess things up live here. So yeah, let's do this. First of all, what is a parser? A parser is basically just piece of software that takes a string of symbols, or it emits a syntax tree out of those, compiles your source code down to bytecode, and then interprets that bytecode like every other interpreted language does. So it does not interpret the source code itself, it interprets the bytecode, and in doing that, it needs to go through some phases. First phase is turning the source code into the symbols, then the symbols into a tree structure, and then this tree, the syntax tree, into bytecode, which can then be executed. That is a parser. The parser is just taking in a string of symbols, outputting a syntax tree. So yeah, like I said, we worked this in 2019 and 2020, and the first question to ask is why? Why was there this need to replace Python's parser? So the first thing to note is that the old parser was an LL1 parser, one of the oldest pieces of software of the Python syntax, like the Python file tree. It was developed back in like 1990 by Guido. And for the most part, it was mostly unchanged for about like 29, 30 years. And yeah, it was an LL1 parser, and that means that the parser can look at the string of symbols, the tokens, and has some grammar rules, some syntax rules. And in order to differentiate between stuff, like between assignments or expressions or if statements or while statements, it can only look one token ahead and nothing else. But Python is not LL1, and that means that there are rules that cannot be parsed by an LL1 parser and need some hacking in order to work. Stuff like assignments, but we'll see this in a bit. Second of all, there was there were some impossible constructs that even with hacking around the parser and doing manual stuff could not work. More on that as well. Third thing was lack of left recursion, and fourth thing was that there was an intermediate representation needed just for the parser. So the parser wasn't emitting the syntax tree directly. It was emitting an intermediate representation and then going into the syntax tree. But let's go into some more detail. First thing is that some rules of the Python syntax are not LL1. What it means is that if we take, for example, the assignment expression rule, which was something that was introduced, I think, in Python 3.8, the walrus operator, you'll see that basically the structure, the rule, the syntax rule that defines this says, okay, what is an expression assignment? It's basically assigning an expression. Wherever you see test, you can think of an expression to a name. But because name appears as the first token of both alternatives over here, that means that the parser cannot differentiate between the two. It only can look at the next token. It can see names on both sides, and that means that it cannot go and deduce which way it needs to go. So in order to circumvent that, we would add some like manual pieces of code, like the one you can see here, where if you see the if condition here, you'll check that we're checking actually the kind of the target. So in the actual grammar itself, we're writing assign an expression to an expression. And then there's a manual step where we're checking that this left-hand side expression is actually a name. That creates a whole bunch of issues, like for maintenance or other stuff or potential bugs. So this was something that we wanted to get rid of. Second thing is that there were impossible constructs, for example, multi-line with statements. Even with using every trick in the book or every hack you can think of, the parser was not able at all to parse multi-line with statements with parentheses around them. Third thing was the lack of left recursion. Now, when you're writing a parser for a programming language, what you wanted to do is to represent the order of operations as well. So order of operations means, for example, that multiplication comes before addition and stuff like that. So when you have an A plus B plus E, or you can think of it as A plus B times C, or whatever it might be, you can, it's not optimal to have like a flat structure like the one we have on the left, which is what the old parser was doing. The correct thing is to have something like the one on the right. And the one on the right is saying basically that we're basically first adding A plus B, and then we're taking that sum and adding C to it. And that represents in the syntax tree the order of operations that are going to be executed. Fourth thing, because of this and some other stuff, we needed an intermediate syntax tree. And for example, A plus B plus C would get first compiled down to this flat structure. And then after the flat structure, we have like a huge file of about 7,000 lines of code. Handwritten code, not generated code, not automatic code, handwritten code that would take this and generate the actual syntax tree that will get passed down to the rest of the compiler pipeline. So yeah, again, not optimal, maintenance, more space complexity and stuff like that. Now, we've covered the why or the basics of the why. Let's go into the how. Back when the project was started, I wasn't there, but I know quite a bit about its history. Guido wanted to play around with pegs. And so we went into this peg direction and just started following. And the nice thing of peg parsers is that remember that LL1 can just see one token ahead and decide which way they would need to go. Peg parsers can look infinitely many tokens ahead. And that's completely a different situation. It's very powerful and you can do pretty amazing things with it. You can just go ahead and backtrack anytime you want. So peg parsers are very easy to generate, turns out, because peg parsers can be written as backtracking packrat parsers, which means basically that you're trying to parse something. If you succeed, then that's okay. If you fail, then you can just backtrack to the original position and try to parse something else. And the code generated for this is very easy to do because it's just a bunch of ifs and whiles, nothing else. So a statement is an assignment or expression or an if statement. And this is just saying, this is just generating a bunch of ifs, nothing else. So very easy to do. Second thing is we can incorporate into the grammar, into the definition of the language, actions, grammar actions. And grammar actions say what needs to be done in case a rule succeeds. For example, here, you might be familiar with a del statement in Python, for example, to delete dictionary keys or delete variable names from the current namespace or stuff like that. So what we have here is the syntax rule for del statements. So you have the keyword del, D-E-L, and then the deletion targets, the things you want to delete. And if this succeeds, then basically what we need to do is emit a syntax token or a syntax tree node that's called _PyDelete. And then this will get passed down to the compiler in order to generate the bytecode. So the immediate representation is not needed anymore from the grammar actions themselves. You can just say, okay, if this succeeds, then we're generating this token. And that's also very, very powerful. Internally, what's being done is basically copy pasting whatever's in the braces into the return value. You can see in the braces on the bottom part that you have a PyDelete, a comma extra. Yeah, some more stuff about open source and a few things that are needed in the context of such a big project like CPython. We need to do testing, of course, and being 100% sure that everything works the way it should be was very critical for us. The only thing we could have a hope of replacing the at the time current parser was if the two parsers actually generated the exact same thing. And so we started by testing both parsers on the started library, which is like 1,500 files long. And just parse the standard library with both parsers, compare the two trees, and if there's a match, then that's okay. If they're not matching, then that means we have a bug and we have to figure out what's going wrong. But this was not enough. You might think that 1,500 files are enough, but they aren't. And so what we did is basically used the Python ecosystem to test the parser as well. So we went out to PyPI, and PyPI is the registry where you pip install packages from. And we downloaded all of the packages, like the top 4,000 packages or top 3,800 packages, and did the exact same thing. Parse the package with both parsers, compare, and fix bugs. So after that, we were pretty confident that everything worked fine. Second thing was performance optimization. And performance optimization was something we needed to do because when we proposed to replace the parser, we vouched that it wouldn't be slower than the old one. And the thing we did here has to do with how pegs work. Remember that alternatives in pegs are ordered, and that means they get tried out in order. So for example, if you have a rule that has 5 sets of alternatives, you'll first try out the first one. If it fails, you'll go to B. If it fails, you'll go to C until something succeeds. And if nothing succeeds, then that means you've got a syntax error. And so it makes sense in order to optimize to basically the things that get visited the most needs to be at the top of a rule, because that means that statistically speaking, most programs will be using those kind of structures. And if most programs are using those kinds of structures, that means that you'll get to parse them first. And that means that for most programs, you're going to be as fast as possible. And again, we did some analysis on the started library to find out, okay, what are the most commonly used syntax rules or syntax structures, and we came up with the order you can see on the right. For example, a statement is either an assignment or an expression or a return statement or an import statement or stuff like that. In an open source context, you also have to have like a very robust release schedule. So what we did is we introduced the parser, but still defaulted in the old one in the 6th alpha version of 3.9. Then by the beta versions, we defaulted to the new one, but you could still fall back to the old one in case you found bugs or whatever. 3.9 was the first final release with the new parser, and Python 3.10 was the point where we were able to remove the old parser and basically lift all restrictions and implement all the nice things we could implement, because the old parser wasn't there. We didn't need to adhere to any LL1 rules, so we could basically implement everything that I showed you before. Yeah, that's mostly it. And now comes the fun part. Now comes the part where basically what I'm going to try to do is recreate a peg parser from scratch in Python, generating Python code. I hope it works. Let me check which one is correct. So this is it, I think. Can you all see my screen? Yes, no? Okay, let me stop the share and try to do it again. Okay, I think this works now. Yes, all right. Great. So let's see. What we're going to be doing is basically creating a parser for, let me try to get this as big as possible. Okay. All right. We're going to be trying to create a parser for a calculator. And so we're gonna see over here, and why calculator? Because there are thousands of them out there, and why not create a new one as well? And yeah, calculator is a very nice example of a very simple grammar. You can see here that you have expressions, you have additions, you have subtractions, you can parenthesize stuff to mix up the order of operations. And ultimately, what you can add or subtract or parenthesize are names and numbers. So this is going to be divided into 2 stages. First thing we'll need to do is basically parse this file and generate something that Python can read, so that it gets to generate Python code afterwards in order to read expressions that adhere to this grammar. So we have a grammar here. We're going to be parsing it. We're going to be creating rules. I have prepared some boilerplate for this. We're going to be creating rules and alternatives out of that grammar. That's going to be the first stage. So what is a rule? A rule is basically everything that's indented together with a name. So a rule is a name, it's a colon, a new line, and then a set of alternatives. And what is an alternative? It's a bunch of items. And after the bunch of items is a grammar action, which again, what is a grammar action? It's what needs to run in case we succeed with parsing this. As you can see in the expression grammar here, every token that there is here, and remember, token are these symbols that the tokenizer emits, that the lexer emits. Every token here, like the name and the vertical bar and the braces and the colon and everything here, is valid Python syntax, or not exactly valid Python syntax, but the tokens themselves are valid Python tokens. And so what we can do is use the Python tokenizer to tokenize this. So what we can do is basically say, okay, we're going to use the tokenize module, and we're going to generate tokens out of this file. First, we need to open the file, of course. So I'm going to be opening data expression.gram, and then we can do this. Okay. And if what I can do basically is go ahead and print that. So we could say for token in tokenizer print the token, which would be which would probably, oops. So okay, this is spoiling stuff. Let's clear it. So yeah, parser gen .py. Oops. There you go. And now we have basically the tokens, and there are many tokens in this file, so we won't go through them. But yeah, we can use those tokens to parse the file, right? And so the thing is that I said before that pegs have an infinite buffer token, an infinite look-ahead buffer. And that means that in order to have that, we need to cache the tokens that the tokenizer give us. So what we're going to do is basically wrap this in a tokenizer class that we write in our, by ourselves. And the tokenizer class, what it's going to be doing is basically take the token generator that we instantiated in the bottom, and it's going to keep a cache of the tokens. So so we'll have a list where tokens will be cached, and we'll also have the position in the tokens buffer. And that is tremendously powerful, because what this gives us is the ability to move back and forth in the buffer as we wish. So we can go as far forward as we need, and we can always backtrack as far backwards as we need. And that is very powerful. We'll see why. Okay, we've got the tokenizer in place. Now we need to write the actual grammar parser. So we'll have a grammar parser that will accept the tokenizer. And what the grammar parser is going to be doing is basically take those tokens that we've emitted from these things and create those rule and alt instances that will later be used in order to generate the Python code, right? So first thing we need to do, we need to define, okay, how are we parsing this file? This file basically consists of rules, right? So a non-empty set of rules and an end marker. And you can think of an end marker like an invisible token that exists in the end of every file. So what we'll need to do here is say, okay, we have a list of rules. And while you can parse a new rule, you can just append this rule to the rules buffer we have. And if the rules are not empty, because remember, it's a non-empty set of rules, and we have an end marker after this, then that means we can return the rules. And if that fails, we will return none, and that will signify a parsing failure, right? So, so what we're doing is basically, okay, we're calling another function that will parse a rule, but in principle, it's a very simple thing where what you're doing is basically trying to parse something in a while or in an if, depending on whether you're in a loop or not. If it succeeds, then you return this set that you've parsed. If it fails, you return none. One more thing we need to do is basically be able to backtrack. And in order to do that, we need to basically figure out where we're at a certain point keep a checkpoint there and be able to always backtrack to it. So at the beginning of every function, we need to basically call this mark function. And what the mark function is going to be doing is keeping track of the position we're currently at. Mark is not implemented, so let's go implement it. It's calling mark on the tokenizer. And what is this? This is doing is basically just returning the position, right? So we just need to know where in the tokens buffer are we. After that is done, then what we can do is basically reset back to this position after everything has failed. So if we don't return rules, and if these rules fail, we need to backtrack into the original position. And how do we reset? We reset by going here and say, okay, now bring the position back to the original one or to the one we pass you. The expect is also not implemented. And what does expect do? Expect says to the parser basically says, I want to get the next token, and I want to verify that the next token is of this given type. And so in order to do that, we need to actually be able to get the next token. First, we're going to be implementing pick token, which basically picks at the next token, but does not advance the position. And so in order to do that, we need to see if we've exhausted the tokens array. If we've done so, then that means that we'll have to append to it. So we'll have to append to the tokens array. Yes, what we're going to append, we're going to ask for the next token from the tokenizer. Else, we're going to be returning the from the tokens array and at the current position. So this is what picks at a token. It sees if the tokens buffer has been exhausted. If it has, it generates the next token from the tokenizer. If it hasn't, it just returns the new the token from the token buffer. And what get token is doing is basically just calling pick token. It picks at the next token. It advances the position as well, and then returns the token. And now expect is very easy to write. What we need to do is basically pick at the token and check if the type of the token is the same as the type we're requesting. If it is, then we're calling get token in order to advance the position as well. If it's not, we return none. Very simple stuff. Every time you need to keep in mind, if something fails, we return none. If something succeeds, we advance the position and return the current token. So now everything works over here, and we've successfully parsed the rule, although not exactly parsed because we have to implement the rule method as well. Okay, let's see, what is a rule method? Again, remember, it's always about keeping track of the position, parsing, and resetting back to the position in case something failed. So we need to keep mark of the position. And then we're going to have a multi-line if, and we're going to have, like, we're going to expect a name token, right? Because all rules start with a name. Then we're going to be expecting a column token, then expect like a new line token, and then expect what was it? Oh no, we're not expecting anymore. We're just calling the indented outs rule, and we'll see what that is. I see that there is a question, and I'm going to answer right away. Give me just one moment. So what this will be doing is return a rule that has the name that we've parsed, right? And the alternatives that we've parsed. And if all fails, then we're going to be resetting to the original position and returning none. And that's it. Nothing more than that. So yes, that is it. Okay, let's see. One question. Is token being stored into a stack? I'm not sure what exactly you're talking about. Is it the tokens? Is it the tokens that we've tokenized? If so, then it's not exactly a stack. It's just a buffer, and we can arbitrarily move back and forth in that buffer. It's not a first in, first out thing, last in, first out thing. If you're talking about like this token over here, it's part of the Python standard library, and it just gives us names for all of the ints that represent the different tokens or token types of Python. So you have some things like colon and comma and semicolon and plus and minus and star and stuff like that. That is it. We're not going to go with the indented alts and rest of the stuff. It's all going to be the exact same structure. It's about basically keeping track of the position, trying to parse an alternative with whiles or ifs, and then just returning the something in case you succeed, backtracking and returning none in case you fail. So yep, that's it. Okay. Okay, indented alts, all of this I'm going to cheat a bit here, and I am going to be taking all of this from a cheat sheet I've got prepared, because it's the same exact thing, and no need to do it again. And yeah, right now we have a grammar parser, right? And now if we can get the rules by calling like the first rule, which is start, and then we can say, okay, this is none. That probably means that we have a syntax error in grammar. If not, then and we're gonna exit. Oops. If not, then we can just print the rules, right? And just print the wrapper for now. So, okay, let's see. If we execute this, oh, there's a syntax error in the grammar. And that means that probably we've done something wrong in the parser, but that's okay. I'm prepared for this as well. So I'm going to come over here. I'm to be doing this, and now it should probably be fine. Oops, no, it's not. Okay, let me see if I've done something wrong over here in the tokenizer. I told you it would be fun to see me fail live. Oh, what we need to do is over here. Remember that we're expecting either a token type or a string, right? So when we're expecting a string, comparing with a type is not enough. We also need to compare with the string. And probably this will work. No, it won't. So that's okay. So what I'm going to do is basically take all of this. And maybe copy paste this into here. Okay. All right. We did have a small error. I'm not sure what it is, but that's okay. Let's go forward. Okay, so you can see now that over here, we've parsed the actual grammar. We've parsed the grammar into like a bunch of rule classes or instances of the class rule. And now what we can do with that is basically write a generator to read these rules and to generate Python code for it. So we're gonna open like a new file that we're going to be writing into. And what we're going to be doing is writing a generator. And this is going to be called generator, okay. We're gonna pass the rules and the file, and we're gonna call generate on it. And this should actually basically generate Python code that can parse expressions that adhere to this like calculator syntax. So generator, what do we need to do here? We have like rules and we need to set this up. We have file, we need to set this up. And first of all, we need to like print into the file, right? So we're gonna do our custom implementation of print. And what this is going to be doing is if text is none, then we're just going to be printing into the file an empty line. And if you don't pass anything to print, then an empty line is printed. Else, we're going to be printing the text into the file. Right? So right now, we can just go to generate and say, okay, we're gonna print something into this file. And I've prepared a header with a bunch of imports and a trailer with making the file an executable. So what we can do is basically print the header into that and the trailer into that, and then just print like a hello or something there. And if we actually generate that, so file is not defined, something is wrong, okay. And yeah, if we now open like the parser.py file, you'll see, wow, we've generated some code by just printing into a file. So the imports, the header, the trailer, and the hello in between. So what we're gonna do here is basically, okay, say, after the header is done, let's print like an empty line, and we need to print a class, which is going to be called generated parser. That's going to be deriving from parser. And then we need to indent, right? We need to indent everything on the right there. So what the indent is doing, we need to keep an indentation level over here. And this is going to be 0 at first. And indent is going to be like a context manager. And what this is going to be doing is say, okay, I'm going to indent by 4 spaces. So we're going to add 4 spaces there. We're going to yield back to the context manager and finally just remove the indentation. And now if we go and here in print, we need to say, okay, if we've got indentation and it's positive, then that means that we need to have some spaces at the beginning of the line. So we'll have like the text now is not only the text that we originally had, it's also like a couple of spaces, right? So we're gonna do self-indentation times spaces to add 4 spaces at the front. So now we can just do something like with self-indent and just write rules, right? And just write all the functions for all the rules. So for rule in self.rules, we can just visit the rule. And then we're gonna print an empty line, and that's basically it, nothing else. It's just printing a bunch of stuff, carefully crafted stuff, yeah, but just a bunch of stuff into a file. And the question that might arise is, where does this visit come from? I've implemented like visit rule and visit out and visit string because there's rules and there's alternatives, and we need to visit those. And we're going to implement something called the visitor protocol. So the visitor protocol is this. Basically, we're going to, what are we visiting? We're visiting a node, right? So here we're visiting a rule. From this rule, what we can do is basically take the class of the node. And this is very cryptic stuff, but it works, which is what matters. We'll take the name of the class, and for a rule, it will be like uppercase rule as defined over here. And then we can look for a method that's called visit underscore and the class name, right? And then we can create a visitor out of it. We can create a visitor out of it, which is going to be like a method of the current class that's called visit underscore something. If there's no such thing, we'll call self-generic visit, which just raises not implemented error, and we're just going to call the visitor. And now, depending on the type of the thing we're passing into visit, we'll either call visit rule, alt, or string. And because I don't have much more time, I'm going to copy paste stuff in the visitors. And okay, where are we? Over here. So we're going to do this. And now if I run this, we should have a completely generated class that will parse this expression grammar. And this is all Python code, valid Python code that basically parses this. And if I create hello.py, hello.py and add a 1+1, then hopefully, if I run my PEG parser with that as input, I'll get an AST node created. 1+1. If I do 1+1+2, then I'll get a binary operation. Oops, I need to save that. A binary operation plus, I'm sorry, a constant 1 plus another binary operation. And we've done it. I have here some files that show like the actual Python parser. This is the whole grammar. Remember, we had to do with like a 12-line grammar. The actual Python grammar is like 1,200 lines. The actual parser is like 39K lines. But yeah, it's basically the same concept. So yeah. That was everything, folks. Thanks for tuning in. And I hope you had fun with this very extreme way of doing things. And yeah, I'll stick around for any questions you might have. And feel free to reach out. Thanks a lot. See you soon. Bye-bye.